All right, welcome back, everyone. Today, we're jumping right into a detailed explainer on thermal efficiency. Specifically, we're doing a step-by-step technical postmortem. If you're an engineer, a plant operator, or just someone fascinated by the sheer scale of industrial power generation, you already know that keeping a power plant running efficiently is really a game of microscopic margins. Today, we're looking at a specific 600 megawatt unit, and we're going to completely tear down the maths, the telemetry, and the physics to see exactly how clean its condenser really is. Okay, let's get into it.
Okay, so before we get buried in the data, let's do a quick primer on how a condenser actually works in a power plant, especially for any junior team members tuning in. Think of a condenser as a massive, absolutely critical heat exchanger. It's physically connected directly to the exhaust of the low-pressure, or LP, turbine. Its one and only job is to take the spent exhaust steam leaving that turbine, cool it down really rapidly, and condense it back into liquid water. But why? Well, because condensing that steam shrinks its volume so drastically that it creates an incredibly powerful vacuum. That vacuum literally pulls the steam through the turbine blades, which maximizes the mechanical work we can extract from it. Without a strong vacuum right there, the whole plant's efficiency just totally tanks. So here's our roadmap for today's explainer. We're going to start with the basics of the failure cascade to see what goes wrong. Then we'll dive into the raw telemetry data, crunch the numbers in the thermodynamic math pipeline, unveil the final cleanliness verdict, and wrap up with a pretty critical look at system fragility. Let's kick things off with Section 1, the basics and the failure cascade. To really get a sense of the physical scale here, just take a look at this overview schematic for our 600 megawatt unit. You can clearly see the massive lower and upper shell structures, right? And check out those critical water boxes on the right side, where the main cooling water actually flows in and out. I mean, we aren't just talking about a hypothetical box on a whiteboard. This is hundreds of tons of metal and thousands of internal tubes, where the heat exchange literally happens. Grounding ourselves in this physical hardware is super important before we look at what happens when things start to degrade. Because honestly, things absolutely do go wrong. The failure cascade all starts over on the left with tube fouling. We're talking microscopic scale, biogrowth, maybe some silt building up on those heat transfer surfaces. It's kind of like plaque in an artery. That buildup creates thermal resistance, meaning the heat transfer drops and the steam just fails to condense at the designed rate. That leads straight to steam accumulation, which kills our condenser vacuum and actually pushes back pressure onto the turbine. The final result? The turbine penalty. The enthalpy drop shrinks, your heat rate shoots up, and suddenly you're forced to burn way more fuel just to maintain that exact same 600 megawatt output. The cleanliness factor we're calculating today measures our active efficiency against a perfectly clean state to stop this exact cascade from happening. All right, let's shift our focus from the theory to the reality on the ground. Section 2, telemetry data. So where are we actually getting our numbers? Look up at the top of the condenser schematic here. Notice we have 4 vacuum transmitters, A, B, C, and D. Now, our math is incredibly sensitive to the vacuum delta. So among these 4, transmitters C and D, or VAC C, actually recorded the highest pressure, and we deliberately selected it as our reference point. You might be wondering, why pick the worst case scenario? Well, to make sure our calculations are conservative and totally defensible. By taking that worst-case, highest pressure reading, our final cleanliness assessment becomes practically baseline proof. We're not artificially inflating our success here, for sure. Let's see how this telemetry builds out our diagnostic matrix. Here, we're contrasting the theoretical design baseline against our actual unit telemetry, both stabilized at a 600 megawatt load. As you can see, our actual vacuum is sitting nicely at a lower pressure of 0.060 bar. But look at the bottom row, the cooling flow. The actual telemetry is showing 92,500 cubic meters per hour. Guys, that's an 8.6% positive variance above the design flow. The crucial takeaway here is that this excess flow massively improves waterside heat transfer, and it's going to heavily influence the rest of the math we're about to do. And of course, we can't just ignore Mother Nature. During this specific assessment, the July rainy season was diluting the seawater. That dropped the salinity from 35 PSU all the way down to 18 PSU. And it raised the temperature. This directly alters the seawater's density and its specific heat capacity. Notice how the specific gravity drops to 1.009? We actually have to multiply our volume flow by this specific rainy season gravity to get our true mass flow of just under 26,000 kilograms per second. These exact inputs are mandatory. If we just lazily use dry season numbers right now, our entire heat rejection profile will be completely wrong. Okay, with our telemetry locked in and environmentally corrected, it's time for the heavy lifting. Section 3, the math pipeline.
First up, the log mean temperature difference, or LMTD. This basically charts the thermal gradient right through the condenser. That orange line at the top, that's our steady steam saturation temperature sitting at 36.16 degrees Celsius. The blue curve traces our cooling water. It enters at 28.4 degrees, absorbs the heat from the steam, and rises to 34.3 degrees by the time it exits. By plugging these temperature deltas into the LMTD formula on the right, we get a normalized thermal gradient of 4.130 Kelvin. And let me tell you, this is the absolute driving temperature force of our entire condenser.
Next, we calculate the actual heat duty. Basically, how much raw thermal energy are we actually moving? We take that highly accurate mass flow we figured out earlier, combine it with the specific heat of our rainy season seawater, and multiply it by that cooling water temperature delta of 5.9 degrees. The result? 624.7 thermal megawatts. When we compare that against the design duty, we get a duty ratio of 93.11%, which means the plant is efficiently rejecting the exact amount of heat required for the current load. Perfect. Now for the most critical math of all. The U values, or heat transfer coefficients. On the left, we calculate our actual performance based on the heat duty and LMTD we just found. That gives us an actual U value of 4,273.7. But look over at the right side, the baseline. The original clean design U value was only 3,946. So why the big difference? Well, remember that 8.6% extra cooling water flow we noticed earlier? We have to run that through a flow correction engine. Higher flow means higher turbulence, and turbulence naturally increases efficiency. So we apply a correction factor of 1.068 to the baseline. That raises our expected clean performance up to 4,213.8, which beautifully matches the reality of our current high flow state. All right, the math pipeline is complete. All the corrections have been applied. Time for section 4, the final verdict. Drum roll, please. By dividing our actual heat transfer coefficient by the flow-corrected expected coefficient, we get a final cleanliness factor of 101.42%. Seriously, this condenser is operating in an essentially spotless condition. We've detected absolutely zero significant thermal fouling. The tubes are clear, the heat is transferring perfectly, and the unit is running at absolute peak thermal efficiency. To really validate this, let's map our math onto the manufacturer's actual condenser performance curve. If you take our duty ratio of roughly 93% down on the x-axis and trace it up to our cooling water inlet temperature curve of roughly 28 degrees, the intersection theoretically predicts an absolute pressure of about 6.0 kilopascals. And what did our physical sensor telemetry read earlier? Exactly 0.060 bar, which is exactly 6.0 kilopascals. The theoretical physics and the physical sensors are in perfect alignment. You love to see it. Now, I know some of you are looking at that 101.42% result and thinking, wait a minute, how on earth can something be over 100% clean? That's physically impossible. It's a great question, and this slide decodes that exact anomaly. When the manufacturer designed the baseline, they baked in a 5% contractual O&M plugged tube margin. Essentially, they assumed 5% of the surface area would eventually be taken offline for maintenance. However, because this specific plant is so highly maintained, all 100% of the tubes are currently active and unobstructed. See that orange block of tubes in the diagram? That is a physical heat transfer surplus. It drives the pressure slightly lower than the baseline expects, which mathematically pushes our apparent performance just over that 100% mark. So we've celebrated a perfect cleanliness score. But before we wrap up, we really need to pivot to our final section and talk about a serious operational warning: system fragility. I want you to see just how delicate these calculations actually are. Check out this sensitivity chart for vacuum pressure. Our actual baseline was 0.060 bar, giving us our 100% clean factor. But what if our vacuum sensor is out of calibration by just one single millibar? If it reads 0.061 bar, literally just 0.001 high, our cleanliness factor plummets to 93%. That triggers a totally false dirty flag and could lead to millions in unnecessary maintenance. Conversely, if it reads just 1 millibar low, the math spikes to 111%, which is a physical impossibility. This extreme fragility totally validates our earlier decision to use the highest recording transmitter just to stay conservative. And guys, this fragility applies to temperature as well. A mere 0.1 degrees Celsius variance in our cooling water outlet temperature swings the entire plant's cleanliness assessment by several percentage points.
So while our final assessment is that Unit 01 is completely free of thermal fouling, I really want to leave you with this metrology warning. Given this extreme mathematical sensitivity, routine and rigorous sensor calibration isn't just a good practice, it's absolutely the single most critical factor for future monitoring. All of our beautiful thermodynamic math is completely useless if we can't trust the sensors feeding the pipeline. So, are your unit's sensors calibrated precisely enough to tell the truth, or is a tiny decimal error currently hiding a massive efficiency loss in your plant? Definitely something to think about the next time you look at a control room dashboard. Thanks so much for joining me on this explainer, and I'll see you on the next one.